Good afternoon. We're going to talk about how to do entity resolution for the best outcomes on your data, how to build composable ER systems. My name is Ninad Sohoni. I'm a delivery solutions architect for Databricks. So I work with customers to build solutions that build systems similar to these and other ML and Gen AI systems. The forward-looking statement, so everything here is informational, consume at your own risk. If you have sat through a few talks today, you would have seen this already. Wouldn't go through it now. So here's what you're going to cover. Entity resolution, we'll do a brief introduction, the what, why, and how, the basics. Then we'll go through a few challenges, and we'll go through solutions for those. We'll also look at a system that demonstrates entity resolution in action, and we'll do a few quick takeaways. Let's start with a simple example. We see a picture of a headset, and there are a few descriptions to it. It's either a Plantronics Voyager headset, or it could be a Poly Voyager, could be an HP Poly Voyager. Which one is it? If we had to figure out, looking at different websites, whether we are looking at the same product or not, how would you figure this out? We ran this through a few models, and they all gave us different answers. So the question then is, which model do you trust? How do you evaluate it? So let's start with the basics. We'll do a quick introduction, and we'll get back to that example. Here we have the core systems that compose entity resolution. We have a system that is in charge of your canonical data set, so that's your master data set that's supposed to deduplicate your records. And then we have a system that's interfacing with the world. So when records come in, this is what's going to check which records do we already have, which ones are new, and going to respond to that incoming request that you've already seen this record, here's the ID, here's a new one, and so on. Why do ER? When we think of ER, we think of very narrow use cases, traditionally, like customer 360, or I had a use case where we had customers from different citizens from different counties getting services from different government entities. And the government agency wanted to figure out which citizens are going where, so they could better understand the needs of their constituents. That's one example. As data has grown complex over time, so have use cases. Now we have examples all across the board where an example use case is, if you want to do fraud detection, how do you figure that out? Or if you have supply chain SKU rationalization, how do you match entities across the board so you figure out where you are maybe buying the same entity in different quantities and you can bulk order and save some money, make the supply chain better. On average, this is costing organizations a lot of money. And the reason that organizations are spending a lot of money is that if you get this wrong, that really is the gateway of your entire company's data estate. This is foundational. So bad data in leads to bad decisions, leads to bad outcomes. Cleaning up data after the fact is not trivial. So it's good to have systems in place to ensure that good data flows in. And if inevitably, when there are duplicates, how do you figure out which ones are the duplicates and clean that up? We have seen, working with customers, ER systems being implemented in a variety of ways. There's a lot of vendor software out there. The recommendation is generally, if you find a good match, you should go and implement that with the vendor. That's the easy thing to do, and it gets you off the ground quickly. We have also seen customers where they have use cases that don't fit well with the vendor software that's offered. So these might be use cases where you want to match specific service records with different products or services that you offer, and maybe the system, vendor system that you get isn't good at that particular use case. So we have seen people build these out. There's lots of popular libraries to do that. A lot of them are open source. So ones that you see here are Zhang or Splink, which is fantastic. Rapid Fuzz is very popular. It's the successor for Fuzzy Wuzzy. Here's the overall system, the way it could look like today. There's two main systems on the right and left, and there's one subsystem at the top. So the main system on the left is the data mastering system. That's where all of your data is mastered. That's where you maintain your golden records. So all the canonicalization happens there. The system that's interfacing with that is where all of your customers or clients or internal services look for matches to data. So that's the system on the right. That's the matching system. At the heart of both of these systems are similar algorithms. Generally, they are the same, but that doesn't have to be the case. These systems have different SLAs. You want your matching system to be fast and responsive. It's okay in some cases to have the mastering system be a little bit slower. So basically, if you think about the matching system, that's more real time. The mastering system, the golden records, the canonicalization, that can be a batch process that runs nightly or on a less frequent basis than real time. Then more and more with the rise of agents and Gen AI, we are seeing enrichment systems that interface with both these systems. So when data comes in and some attributes on that data are missing, we have the opportunity to go out and get those attributes on the fly when we do matching. Or you can also do that after the fact, build a separate system as a source for references, and then use that system's information to deduplicate records. So maybe your sources aren't sending you the full record, but you can enrich that in-house by implementing these systems. So three main systems, three different SLAs, slightly similar algorithms for figuring out what is the entity we are dealing with. How do you match it? We'll start with a relatively simple example. We have records of two people. Hopefully, they are the same person. But these records have attributes. So we have the first name, last name, address. Matching names is common. Historically, this has been done with soundex or other phonetic algorithms with distance, string distance techniques like rapid fuzz, Levenstein, which is built into Spark. The crux is it does calculate edit distance between two relatively similar attributes and gives you a value. So in this case, we see that the system might tell us Robert and Bob are maybe like 70 or 80% similar. The last name matches perfectly, so there's a perfect score there. And addresses get a little bit tricky because you have variations in address 1, address line 2. Maybe some elements of address are missing altogether. So in that case, you have the opportunity to look at address string as a whole and calculate the string matching distance there. It might or might not be very reliable. We can also break it out into parts. Separating out zip code at the end is relatively straightforward. You can separate that out and then do a matching on that. And all of these translate into features that you can get scores for. So you're doing pairwise matching between features in two entities. They give you a score, and you can do a composite score any way you like with rule-based algorithms or maybe with machine learning algorithms if you have labeled data. The algorithm spits out the answer whether these entities are the same or not, and that's the algorithm's best guess. Let's switch to a slightly more modern example where the types of data have changed. We have the same kinds of attributes as before. We are trying to match between two entities, but now besides the simpler attributes like ID, we have names which are more complex. We have descriptions which can run into long paragraphs, and we might as well have images. So how do you figure out if these two records are representing the same thing? ID matching can be the same as before. You can do an edit distance and get some signal of whether this is the same thing or not. Name matching, if you have relatively shorter names, string matching might work, string distance might work. For descriptions, though, string edit distance techniques might not work as well because, you're getting garbled messages out of that. It's not reliable to figure out whether these are the same thing or not. For images, how do you compare those images? We'll take a step back and see some techniques of comparing attributes, some more recent techniques. The first one is just edit distance. So all of your string matching, fuzzy wuzzy, rapid fuzz, Levenstein, all do this or some variation of this. This literally gives you what's the difference between one string and another, and you can normalize that by the length of one or more strings. So you get some sense of they are 80% similar or 90% similar. The second thing is a bag of words based technique. So we collect the vocabulary of all words across all records that we have seen and figure out which words are common in that vocabulary. These words don't have much meaning in figuring out entities. It's the rare words, like Orion in this case, which you would expect to be rare across a list of products, that would carry more weight as to this is an indicator of or a signal of a match. So these techniques, they start with a bag of words or an inverted TF-IDF collection, and based on that, you can carve out vectors. So the sentence or the entity is represented as a vector at the end of the day, and then you can apply algorithms to measure distances between vectors. Simple techniques like Euclidean distance or cosine similarity help there, but the difficult thing is to get all of your text or data converted to vectors. The technique on the right is similar. It's all of your embedding models. Here the example is I was trying to figure out whether addresses carry any semantic meaning. We were trying to match address data, and my worry was that addresses don't really have any semantic meaning. How would language models figure out whether they are the same thing or separate? So what we're looking at in the blue and red is one of those are really address records, but the second thing is concepts like water or apple, and the address records have those words which have meaning in common language in the record itself. So if you have something like 123 Water Street, does the language model conflate that with the concept of water, or is it able to treat that as an address? And the separation here indicates that it's able to do that. So it bunches all of the addresses together, it bunches all of the concepts together. Now this is still a projection of a high dimensional space into 3D. So these models have more separation possibly between these concepts than we are seeing in the picture here. Now we have more techniques basically to take entities, strings, and convert them into vectors. Based on vectors, we can now do the comparison that we were seeing on the products before, right? We get a name, we can convert those to vectors, we can compare vectors with cosine similarity or Euclidean distance. We can get a description, we can run them through TF-IDF or embedding models, get a vector, compare those. So at the end of the day, just as before we have a list of features, we just arrived at them differently. We can run those features through rules. We can run them through an algorithm, like if the name is 80% similar or more, then maybe treat that as a match. We can run them through machine learning algorithms, and then we can conclude whether they are the same or different. So there are a few challenges as data gets more complex and bigger. The first one is scale. This is a fairly known issue, but it's represented here in this picture. As you have more and more data, when you try to match incoming data against your existing data, or it can also be your existing data against itself to deduplicate, it grows quadratically. So you have to do more and more computations as your data size grows. And this is just the number of records being compared, right? You're really comparing attributes within those records. If your data have like 10 attributes, that's 10x the number of comparisons. But with the embedding techniques or bag of words, when you have vectors, there are algorithms that can do approximate nearest neighbor search in a vector space. It gives you an answer based on searching a narrower space than if you were to do everything against everything. So this, in a sense, takes down the complexity from O of m into n or n squared or n factorial if you are doing deduplication to O of n in a sense. One thing to call out here, it depends on how you implement your technique. So with TF-IDF or something else, you still might get a lot of matches that you need to sort through. But with vector search or other techniques based on embeddings, you can ask your vector database to give you just the top 10 matches. So it kind of constrains the search space when you're trying to do matching between two entities. So here's the typical search pattern. Now that we have this complexity of trying to map our entity to a vector space and then try to do comparison between vectors. We start with some sort of a blocking technique to reduce the number of comparisons we have to make. Historically, this was based on similar attributes, like first names start with the same 3 letters, then you consider those for a match, or like at least candidates for a match. Could be based on zip codes. For products, it gets more tricky because you don't have like names. You have names, but no zip codes and other attributes that you can easily classify things into. So basically, you run them through some sort of an algorithm, figure out the comparisons you would wish to make, and then send those on to a more fine-tuned algorithm that's either doing pairwise matching, like a machine learning classifier, or maybe even an LLM. This can be implemented in a variety of ways. In this example, we have candidates being fetched based on exact matches on name or partial matches on something else, or maybe if they have an attribute like a price, we do a price within some narrow margin. This gives you a bunch of candidates. These are not matches, but they might be good candidates for running a match algorithm on. One way of doing the matching is the Felighi Center algorithm. That's what the Splink framework implements. This is what is going to do pairwise comparisons between your candidates and going to give you a confidence score of whether two things are the same or not. Here's a completely different implementation, and you can mix and match both. The first constrainer of your data or blocker is using hybrid search or some sort of a semantic similarity algorithm to find candidates for a match. Now, once you do have those candidates, you can run them through any machine learning technique or rules-based techniques as before. You can also send them through LLMs, and this basically becomes like your RAG pipeline. There's a few other challenges on evaluating the performances of the system, and I'll pass it over to my colleague to walk through those.
Thanks. Hey everybody, welcome to the session. My name is Yinxi Zhang. I'm a staff data scientist at Databricks. Been with the company for over 4 years now, and happy to see everybody here. Similar to Nina, I work in the field engineering, working with customers to build the solutions. I saw a few familiar faces here. Cool. I will touch upon the challenges of accuracy and stagnancy. The robust system, a robust entity recognition system is relying on how accurate we measure the performance and also how do we monitor and keep a consistent and a continuous development loop. All right, this is one example of a metric that very popular people use in the information system to measure entity resolution modeling results. Mean reciprocal rank. Basically, the higher the rank of the top match in your find it candidates, the higher the score will be. Using this as an example, you can see for the first row, your predicted match have 3 records, and then the top one is matching the top one. So you got a rank of 1, and then as it goes lower to the rows, you see some of them have lower ranks in the predicted candidates. Thus, it gets lower reciprocal rank, and then we do the average of all your input records to get the mean reciprocal rank. The point of here is just to showing you sometimes in entity resolution, order matters. It's not just trying to find all the record within the candidate, it's also trying to make sure the most relevant one comes at the top. But besides mean reciprocal rank, there are a lot of other metrics. We're not trying to recommend one specific metric for all the general use case. It depends on what's your use case and what is most important to your system. Some of the example here you can see some of them are based on pairwise comparison, like precision, recall, and F1 score. And when you get to a more complicated entity resolution with clustering, you can use metrics like B cubed metric, which is just aggregated results of the pairwise metrics. And some other ranking metrics similar to MMR are NDCG at K, those. This is also based on the ranks of the predicted results. I think if you want to choose the best component of metrics depends on your use case rather than relying on a specific one. We're trying to show this using one of the example. This will be shown in later Nina's demo as well. We have built 2 different modeling systems for two records matching, and then you can see one of the model uses bag of words type of approach, and the other uses vector search to do the semantic embedding similarity search. And one actually have like a higher MRR but lower precision. Which model to choose, right? Which metrics matter to you depends on the business use case. This is just one example to show that creating something specific and tailored to the use case is important. And the other challenge Nina mentioned earlier is stagnancy. Your data, the master data is massive. Your model doesn't necessarily updates as the data refreshes. So how do we have a continuous development loop and keep improving the model performance? The key we want to emphasize is to have the feedback system. When you have model in the development stage, make sure some level of offline evaluation has been placed in the entire pipeline, make it part of your CI/CD process, make it part of the integration or even unit tests of the GenAI system, similar to what we will do as software engineering best practice. And this way, whatever changes made to the model go through validation process before it actually get deployed. And once it's actually deployed, you can do like batch or real time, either case, right? In the demo Nina will show later, we actually use a real-time serving endpoint to generate inference results of the models, and you can implement online monitoring for the models where the model, not only the accuracy metrics of the model will be displayed in a dashboard and visualized, as well as you can also track some system metrics like latency and cost to have a holistic comparison across models. The most important thing, I think, is actually to include your human SMEs in the feedback system. Trying to tie this back into the earlier example, if you guys still remember the 3 sets records Nina showed at the beginning of the slides, he actually doesn't mention like what are the true ground truths, right? If you are familiar with the business, familiar with the product, you definitely know those 3 actually are the same item. The reason description and title is different is because HP acquired Panatronics and later changed the product brand name or model name from Panatronics to Poly. So without that business context, it's hard for model to imply that at the beginning. So this definitely takes iterations. The first iteration, a lot of a model will get it. But it doesn't matter, right? We want to have human reviewers in the loop to be able to judge the result and score the result and being able to provide feedback so we can understand which portion of the model or which node in the modeling pipeline went wrong and how can we improve. So this is just trying to tie things together, explaining the continuous development loop. You can have one model that's already in production. This can be your champion model, and making sure we have an eval system. You can use a combination of human judges as well as LM judges. Later on, when Nina showed the demo, we'll also give an example of LM judge records and showing how human judge can be augmented and speed up with LM assistant. And then your data scientists can keep working on improvements of models and iterations. And when there is a new version that's ready to be tested, it could be a challenger model that runs in the shadow mode with the champion model as the complete loop. With that, I think we want to provide a really quick and a simple tool survey for some of the key processes in the workflow. What can you use? what kind of open source tools are available, and of course we are heavily biased towards the system, and we also want to know like how those things can be integrated on the Databricks platform. On the evaluation metrics side, of course, there's a lot of like open source Python package, but what we want to emphasize and call out is that once you have built your custom metrics, you can use MLflow Evaluate API to run the offline evaluation, and it will give you a nice UI which you can visualize everything nicely and having the lineage and tracking information on place. And for human feedback, there's a lot of vendors trying to do like label as well as annotation. On the platform, you can build customized UIs with Databricks apps. The experiment logging of model performance and model iteration can be done with managed MLflow, and monitoring can be done with Lakehouse monitoring. Similarly, with data quality, there are some quality expectation built in with the DLT pipeline, which can scale up your data processing as well as your data validation. For workflow orchestration, when you have like a batch pipeline for your entity resolution, you can use Databricks workflows for those orchestration. With that, we kind of want to summarize what we have been trying to explaining. We have a lot of intro slides leading to the challenges of entity recognition, mainly your compute effort and your management effort scale exponentially as your data scales. You have to use tools that's able to scale with your data. High dimensional vector search is definitely helping in the process, and also compute with Spark can scale horizontally across clusters. For monitoring and keep improving the model performance and accuracy, we recommend you to have a solid evaluation monitoring system and a consistent feedback loop. With that, I'll pass it over to Nina to do the demo.
All right, let's look at an application. For this demo, we are using some product data from the University of Leipzig. This is a popular benchmarking data set, the Amazon Google products data set. So we have one data set which has products from the Amazon website and one from the Google website. We'll take a brief look at the data sets. So we have the name for the product. We have really long descriptions. We're just showing a part of it here. In some cases, we have a manufacturer. In some cases, we don't. We have a price as well. An interesting technique with embeddings and models that are able to understand the data is that you don't have to do feature by feature comparison. You don't have to take names separately and try to create a match and all that. What you could do is package everything together, send it to a vector search model, it will give you an embedding, and then you just compare the entire record with one go. So here, what we'll now do is, let's try to add more data. All of that data was data from the Google website, compiled by the University of Leipzig. What we'll do next is we'll add data from the Amazon data set. So completely separate sources. For the sake of this demo, we'll add a file, but this could be your data ingestion pipeline, which when it runs, it's going to make data available at some cloud storage location. Can be a streaming process as well. In this case, this loaded data to Unity catalog and then pushed it to a Delta table. We'll take a look at the records here. These are from Amazon. They have a similar schema with vector search based models. This doesn't really matter all that much. If some data is missing or this didn't have descriptions or some new information, the model wouldn't really complain. It would try and make sense of that as well. What we can do next is package all of this information into one record, generate an embedding for it, and then compare that embedding for each of these records against all of the records in our system to find matches. So we'll go to the next page, and here we'll click on the match products button. This is going to run a batch process to match all the records we ingested and find records from the Google dataset. This was a relatively small dataset, so it ran instantaneously, but again, like with the scaling with vector search and embedding techniques, you can do this better than with trying to do quadratic complexity matching. Here we see matches from the source, from our source system. Let's see a better view of that. Okay. It's a little constrained to look at, but what we have here is we have the source data from the system, the file that we just uploaded. These are all compressed records. They have the name, description, price, manufacturer, all combined in one record, and that is what was used to try and find matches against your existing data. Give me just 1 second. Live demos. I was trying to test this before the demo. Okay. So when we arrive at this screen, what we have are our source data that we ingested and the data in our system that it found matches to. It gives us a score, so we can rank those in order, and we can still determine whether to run a subsequent model on this or not. In this case, this was just a vector search model, so it just is pure vector search, but it's behind a model serving endpoint. So what you put behind it is up to you, right? You can have one model, you can have an ensemble, you can have a series of models. So all of the configurations that we saw earlier, where you can do different kinds of machine learning rule-based combinations, they're all possible. You can put that and abstract that behind an endpoint, and this will generate the same kind of output for you. So you're not constrained to one model, free to experiment with one champion model and then have more challenger models backing that, where you are continuously running those as well. Okay, so you have generated data. To improve the models, the key thing that you need is ground truth. And that really is the challenge. I've worked with customers where they wanted to improve their RAG systems or LLM systems, other kinds of models. Compiling ground truth is really hard, takes a lot of time, but now we have smart models to help us with that process. Here there is another endpoint which is going to use an LLM to check whether the description on the left matches the description on the right and give us a match or not. We run this. What you put behind the second endpoint as well is up to you. So Yinxi was showing the different signatures from two models on accuracy and recall and precision. These are kind of different model personalities. So you can have a model that's always going to give you an answer. It's going to give you lots of answers as one model, one personality. And a different model that's a little bit shy, it's going to sometimes give you an answer, but more often than not, it's going to give you the right answer. So with that combination of perspectives, you can make a decision of whether this is a good match, it's a match that needs to be reviewed by humans, or you can auto-accept that match. So in this case, all of the data in our system was evaluated by an LLM, and it gave us, for each pair, is this a match, is this not a match? So mostly, our vector search model was good, or at least that's what the LLM thinks, and it sees that most of these things are really the same products. In some cases, it says that, yeah, that's not a good match. You don't have to take the LLM's word for it. You can have like multiple models behind that endpoint, but you can also have humans take control and then say, yeah, that this is not a match. The LLM said that this is a match, but this is not a match. So you can make those changes and have a system that continuously compiles ground truth. Once you have that, that's fodder for your fine-tuning for GenAI models or for classical machine learning models, where you can feed that and improve the quality of models. With that, you can also do more interesting analyses where you can look at where your models differ, and you can kind of package that into a Genie space where you can just go and start asking questions like, what is my data like? What are where do these models differ? So I ran something earlier and got an answer for records where the LLM said one thing, but the model that was making the prediction or the matching was saying something else. So that gives you some insight into where your models might be struggling, or where you would want to put like humans in the loop more to resolve that difference. With that, I will switch back to the presentation, and we'll have some time for questions. So a few key takeaways, points that we felt were new when we worked with customers. Entity resolution models are also machine learning models. They can be experimented with. You can have champion and challenger models. What you put behind a model serving endpoint kind of abstract that model from the business process or the consumption client, and you can have multiple models that you can experiment with, figure out one that works the best, keep on improving it. To improve your model, you need to have ground truth. You can do that by having a human in the loop feedback process, or you can use LLMs to help that process. If you have models with different personalities, so to speak, that especially help with that feedback process. Evaluate models using feedback ground truth. So once you have feedback, you evaluate your models, have multiple models as challengers, and build a modular strategy for different processes. So at the very beginning, we saw that there were 3 different systems. One was the clustering system that was in charge of your golden records. One was your matching system, and one was the third system that was trying to enrich your data. All of these use matching algorithms behind the scene. What you can put in that algorithm is kind of up to you, but modularizing the system and abstracting it behind an endpoint gives you the opportunity to do that. We have a couple of minutes for questions.